Hi there, and welcome to this video. Today we are going to discuss why you need a mathematical model in your processes and, generally speaking, for business. First of all, what is a mathematical model? Well, let's take a look at Wikipedia. A mathematical model is a description of a system using mathematical concepts and language. Well, that's it. And the model then may help to explain a system and to study the effects of different components and to make predictions about behavior. The effects of different components, that means that using a mathematical model, you can understand how your variables are influencing your system, your process, your product, whatever. And you can use a model to predict the behavior of a system. Well, that said, let's switch to some further considerations about mathematical models and mathematics as well. I'm sure you know that once philosophy and physics, they were together. They were two different sides of the same line of thought. The first philosophers were also the first physicists and vice versa. But then suddenly something did change in the past centuries, and the two disciplines took very different roads. And today we perfectly know that philosophy is one thing and physics is another thing. And they are very different, even if sometimes they study the same subject, nature and the universe and behavior of things and so on. But they are deeply and definitely different. And what was the point that separated the two disciplines? It was mathematics, definitely, because physics always uses mathematics. And mathematics as a language for the laws, for the theories, for everything, for predictions. Physics is based on the use of mathematics as an instrument. On the other hand, philosophy does not use mathematics at all. So the difference, the only and deep and uh, ultimate difference between philosophy and physics today is that physics uses mathematics and philosophy does not. Now, why this digression about physics and philosophy? Because I'm quite sure that everybody out there agree with me that physics is science. So, given that physics is different from philosophy only for the fact that basically for the fact that physics uses mathematics, then if you want a scientific process in your company, in your business, then you need to use mathematics. It is mandatory, or your process will be based on philosophical assumptions. If you want a scientific process that is repeatable and reproducible and well known, stable, and of good quality, that means with little variability, then you need to use mathematics and you need to have a mathematical model that describes your process. Well, now let's make an example of what a mathematical model actually looks like. Suppose this is your process, whatever it is, and you have your output from the process, which we call y, and for the sake of simplicity, we have just one input to the process that we call x. So what could be the look and feel of a mathematical model describing this process? The very simplest example of mathematical model could be just this one. Y equals x. We can draw the model. Here it is. Here we have x, here we have y, and this simple model will look like this. This line is our model. This is y equal x. It is our mathematical model. How can it be useful to us? Oh, that's very simple. For example, given the relation, the mathematical relation between y and x, you can know what will be the value of y for any given value of x. Just simply put the value of x in the equation and you will get the value of y. In this case, it's very simple because y equals x. So if x equals 3, then y will equal 3 as well. But obviously, there can be very much more complicated mathematical models. But in every case, the relation will always be used like this. Given the values of my x, what will be the value of my y? And the equation will give me the answer, allow me to predict the behavior of y given the value of x. That means I will be able to know what will be the output of my process given the values of my inputs. And this is really interesting, I suppose. Yes, this is very interesting, I confirm, because usually your process will have many more than just one inputs. Your process will have a lot of inputs, x1, x2, xn, and understanding which ones of your inputs are really significant on the output of the process is not that easy, and there are very common mistakes that are currently made everywhere in every business, in every company about this point. We will talk about this in further videos, but this is the point. It is not easy to understand, given many inputs to a process, which ones are really important to define and determine the variability of your process output, whichever it is. Well, typically, in cases like this one, which are the most common cases, you will get a function, a mathematical model describing y as a function of x1, x2, xn. And in this mathematical relation, you will have only those terms that are really important. This is very interesting because that means that using a mathematical approach, you will be able to understand if, for example, x3 is not important. And if x3 is not important, you can remove from your controls. You can be free from taking care of the values of that variable because it is not important. And this means saving time and materials and so on. So it is definitely important to understand which are the real important variables among the inputs to your process. One of the main topics with mathematical models is that with a mathematical model, you can study interactions in your system. Now, the point is, what is an interaction actually? And we are going through this point using a very simple example that everybody should be able to follow as it belongs to everyday life and that is quite common. So suppose that our process is baking a cake. So this is our process. We are baking a cake. And the output we are measuring is the moisture of the cooked cake. As inputs of the process, we have the time and the temperature. So just two inputs for a simple process that everybody in his life should have seen at least one time, baking a cake. And the output is moisture. Now, here we have four ovens to run our experiment. And suppose the first time we have 180 Celsius degrees for just 2 minutes. What will happen to our cake? Maybe the temperature is okay, but the time is too slow, is not enough to have to have our cake to be cooked as it should. So this is not good. Another experiment that we can run is having our oven at um, normal temperature. For example, the ambient temperature, 22 degrees, for say 50 minutes. What will happen? Nothing at all. But we know that both temperature and time are very important factors in order to cook a cake. Now, suppose that the third time we try with 180 degrees for 180 minutes. What will happen? As a result, I'm quite sure that our cake will be extremely dry, and maybe we will have something very, very black coming outside of the oven because this is too much time for this temperature. Finally, suppose that we have 180 degrees for 35 minutes. Yes, this could work for us. Usually it works 35 minutes, 40 minutes, something like that. Because this is a good combination of temperature and time. So, what are we learning from these four experiments? That surely time and temperature are important themselves, but it is also very, very, very important to understand how we mix their values, because the effect of temperature on moisture, which is our output, our outcome, depends on the value of time. And in a very similar way, the effect of time on our process depends from the value of temperature. This is an interaction. Time and temperature, they are both important, but in our process they interact, and their effect on the output, which is the moisture of our baked cake, cooked cake, depends on the relative values of time and temperature. This is an interaction, and this is something that you can find out and measure and identify and use in your computations only if you have a mathematical model of your process. Well, now I'm quite sure that you're curious about how a mathematical model for our process of baking a cake could look like. And I'm going to show you a very simple and very useful way of creating a mathematical model for our process of baking a cake. Here it is. The mathematical model that we can use for this process is something like this. Y, that is our moisture, equals to beta 0 plus beta 1 for time plus beta 2 for temperature plus beta 3 that multiplies time and temperature. Okay, these betas, here they are just coefficients, and they are numbers that multiplies time, temperature, and their interaction. Here it is. This is the interaction. This is the interaction term that appear in the model, and we are going to discover that the relative value of beta 3 compared to beta 1 and beta 2 is what really determines the behavior of the system. And this simple, very simple mathematical model, which is actually a polynomial, is able to describe the behavior of the system and the effect of the interaction term. Okay, there it is. Let's see it in action. Here we have a polynomial. Here we have called the variables x1 and x2 in place of t lowercase and t uppercase, but it's exactly the same. And in this case, we do not have the interaction term, as you can see. We have beta 1, which is 1.2, and beta 2, which is 0.9. We do not have beta 0, it's not important, and we do not have beta 3 for the interaction. Okay, and this model, which is actually in 3D, 3 dimensions, because we have x1, x2, and y. So it brings to a 3D model that we can see here. This model is exactly a surface, this kind of surface in a 3-dimensional space. And here on the right side, we have the contour plot of this function. The colors give the surface levels. Color is in place of the value of y, which is the third dimension. Well, now suppose that we add beta 3, which is very, very small, for example 0.01, that multiplies x1 and x2. What will happen? A slight change in the surface. As you can see, there is a little bit of torsion in the surface, and this is the effect of the interaction term. On the contour plot, we have a slight change because the lines are no more straight. They are a little bit curved, but just a little bit. Let's see what happens if beta 3 is even bigger. Oh, now we can see definitely a change in the surface. As you can see, there is even more torsion in the surface, and the lines now are no more straight. It is quite evident. This is the effect of the interaction term. And let's see what will happen as beta 3 gets even bigger and bigger. For example, as you can see, what once was a straight plane in a 3-dimensional space is now completely different. And the contour plot representing our model is definitely different. Because as you can see, we have two directions, the ones colored in blue, where the values of y, which is our moisture in the previous example, get lower. And we have two directions as well, the green and orange ones, where the value of moisture is increasing. So the behavior of the system is quite complex now. It is definitely different than a model where we do not have any interaction term. As you can see here, without any interaction, there is just one direction where the moisture value is decreasing and just one direction where the moisture level is increasing. So as you can easily understand, adding a significant interaction term to a mathematical model will lead to very different behavior of the system. That is, if we have an interaction, a significant interaction, the system will behave in a very different way rather than not having the interaction term. So up to now, we saw just two examples. The first one was very easy. Our model was something like this: y equals x. This was a two-dimensional, bidimensional model because we had just one x and one output. That makes 2 dimensions. Then we saw something more complex with our output, our y, which was the moisture of our cake, and this was described as a function of time and temperature. Thus, this was a three-dimensional model because we had two axes and one output. But what happens if our output is given by, for example, time, temperature, concentration, and pressure? This is quite more complex because, as you can see, we have four descriptors, four axes, and one output. This is a five-dimensional space. So while in the first two examples we had the possibility to draw our models and see with our eyes what was going on, here we cannot because we have a five-dimensional space and we cannot neither draw neither try to imagine an object that lives in a space that has more than three dimensions. So can we face such a problem with n dimensions where n is greater than 3? Well, the answer is yes, definitely, because mathematics can work in every kind of dimension and we can study models describing problems and systems existing in every kind of dimension. The mathematics is always the same and the power of these models is always the same. Or maybe when the dimensions are greater than 3, the power of the mathematical approach is even greater because without mathematics you cannot face this kind of problem. You must use mathematics to model something that exists in more than 3 dimensions. So, summing up, we have at least three good reasons to use mathematics in our business, and we have seen them so far. The first point is that if you want to have a scientific approach, you have to use mathematics because that's the difference between philosophy and physics, for example. The second very important point is that with a mathematical model, you can model and study interactions. And as we have seen in the previous example, interactions are really, really important to find out and to study. And third, we have seen that with a mathematical approach, you can model and study even complex systems that you couldn't approach in any other way. There is also an important fourth point that makes using mathematics very, very important. Consider this example. We have our process P and we have three inputs, x1, x2, and x3, and here we have our outcome y. One very common mistake is that in order to study the effect that x1, 2, and 3 have on y, people used to fix 2 out of 3 variables and letting only x1 to vary throughout the experiment. Then, in the next step, you fix x1 and x3 and you let only x2 free to vary throughout the experiment, and so on with x3 and even more variables if you have more than 3. Well, this is a very common mistake, because if you do like this, if you proceed using this one-to-one comparisons, that means one x with one y, just one at a time, there is a theorem that shows that the uncertainty that you gain on the variability of your outcome increases as the number of inputs increases. So the greater the number of comparisons one-to-one that you do, the greater the uncertainty that you have on the variability of your outcome. So this doesn't work, it is obvious, and consider also that if you let just one x free to vary throughout the experiment, you will never be able to study, to model, and to study the interaction terms of your model, because you will never see two variables free to vary together at the same time throughout the experiment. So there are at least four important points that we have seen so far that make using a mathematical approach more than clever. It is necessary in order to study and model your system, and in order to really know what is going on throughout your process.